Okay, hello everyone. I'm Dejun Jiang from the Institute of Computing Technology, Chinese Academy of Sciences. Uh, Now I'm an associate professor at ICT, and my research interests are storage architecture and system. Today, it's my pleasure to be here to give the talk on OpenFlash, a hardware-software co-designed open source SSD controller platform. Because my network is not stable, so I may turn off the video cam to save the network traffic. I'm sorry, I need to first turn off this video cam. Okay, let me continue. So in this talk, I will first introduce why we develop OpenFlash. And then I will introduce the architecture of OpenFlash and its current status. I will also introduce two explorations we are taking on OpenFlash. And finally, I will conclude my talk. So first, why do we develop OpenFlash? Today, SSD is adopted in data center and mobile devices. For example, the most popular NoSQL database, LevelDB and LogsDB, they are using SSD as the underlying storage devices. F2FS is a local file system, which is widely used in mobile phones. On mobile phones, NAND flash is the main storage medium, and UFS-based SSD or NVMe-based SSD are the major storage devices used on mobile phones. As for some distributed storage systems like Ceph and HDFS, we found that they are also use SSD as the underlying storage device to accelerate data access performance, which are used in scenarios such as cloud computing and big data analysis. So SSD is important to today's storage system. However, SSD has unique features. First, SSD has asymmetric read, write, and erase performance. For example, the read latency of an SSD is about tens of microseconds. Meanwhile, the write latency of an SSD is from tens of to hundreds of microseconds. When SSD executes erase, it usually takes a few milliseconds. We also tested the read-write interference for SSD. On this slide, there are 4 figures. These 4 figures show the performance result of read IOPS and the latencies when an SSD receives read and write mixed workloads. The above 2 figures show the 4 kilobytes random read IOPS, and the bottom 2 ones show the average read latencies. The x-axis is the concurrent write bandwidth. We increased the write bandwidth from 100 megabytes per second to 1 gigabyte per second. As you can see in the figures, we found that when write bandwidth increases, the read IOPS decreases, as shown in the above 2 figures. Meanwhile, the average read latency increases with the increased write bandwidth. So it means that because SSD has asymmetric performance, it suffers from performance degradation when serving mixed workload. This is a challenge when we apply SSD to the real storage system. So this is the first unique feature of SSD. And then we can look at the second feature of SSD, is that it requires erase before write. It means that when we write a piece of data into SSD, SSD needs to first erase the data block receiving this piece of data. In order to avoid erase before write, SSD firmware use remapping to execute out of place update. So when updating a piece of data, SSD maps the data into a new location. and the old location of this piece of data become invalid. Then SSD executes garbage collection to reclaim this invalid data. However, the invalid data are usually co-located with some valid data. So garbage collection needs to copy this valid data from erasing blocks and then write them back to SSD. This introduces read and write amplifications. This is also unfriendly to small writes. So here in this slide, we can see this figure. This figure shows the write amplification of an SSD. The blue lines are total write traffic, and the purple lines show the real user data traffic. The gap between the blue lines and the purple ones are large. This gap is write amplification. So in addition to the asymmetric performance, garbage collection is a second challenge when we apply SSD to real storage system. We need to use software hardware code design to address these issues. On the other hand, in recent years, a few new SSD paradigms are emerging. For example, in 2017, Open Channel SSD is proposed. Open Channel SSD exposes internal architecture to upper-level programmers. So programmers can decide the data layout inside the SSD and can trigger garbage collection on the host side. It provides convenience to programmers to control SSD behavior. However, Open Channel SSD requires programmers to be familiar with internal architecture of SSD, which is a heavy burden. In these 2 years, Zone namespace SSD, which is we also call the DNS SSD, is a hot topic. DNS SSD provides sequential writes inside the zones and can erase a zone without internal garbage collection. It attracts many attentions from the storage community. The community hopes DNS SSD can address the classical garbage collection issues. Moreover, near data processing is also a major concern from both academia and industry. Near data processing allows one to offload some computation into SSD, which can fetch data very quickly and save data transfer cost. So we need a real SSD platform to explore and evaluate these SSD new paradigms. Actually, we have some open source SSD platform. OpenSSD is such a platform. OpenSSD includes a Tiger 4 SSD controller. This figure shows the hardware board for OpenSSD. And OpenSSD is built on Xilinx Zinc FPGA. This FPGA has dual ARM core Cortex A9 core and a 1 GB DDR3 SDRAM. The interface of OpenSSD to the host is PCIe Gen 2. And OpenSSD used the Torch NAND interface. OpenSSD provides a few example codes for firmware, which include tutorial FTL, greedy FTL, and dummy FTL. So in my own opinion, OpenSSD is a good platform for us to develop a customized FTL, which can run on real SSD. However, as you can see in the list, the hardware configuration of OpenSSD are somehow out of date, and OpenSSD use ARM core as its processor. So we cannot do much to the processor, which may be useful in providing customized processor or accelerations for near data processing. So we want to conduct some system research based on real SSD platform. For example, we want to implement and evaluate SSD-related novel ideas on real SSD platform. We want to explore new protocol and specifications like the DNS SSD I just mentioned. And also, NAND chips are continuously developing. When building storage system based on SSD, we want to explore features of underlying NAND chips, such as delayed erase, out-of-band area, and partial read and write. Finally, in order to provide near data processing, we can fully utilize RISC-V to design SSD domain-specific processors or hardware accelerators. So in order to meet the mentioned requirements, we propose OpenFlash. This is a hardware software co-designed open source SSD controller platform. We hope this platform can be used as a research platform for exploring novel SSD techniques on controller and storage systems. So that's why we develop OpenFlash. Okay, next I will introduce the architecture of OpenFlash and its current status. This figure shows the architecture of OpenFlash. As you can see in this figure, we have a RISC-V-based processor, which runs SSD firmware. We have a MEME controller. This provides the interface to the host side. And we developed the flash controller to process read and write requests to the flash chips. So far, we open source 3 key components, which are RISC-V-based processor and flash controller and the FTL firmware. Right now, OpenFlash can run on 2 FPGA platforms. The first platform is Xilinx ZC706. It has similar configurations with OpenSSD. For example, it has dual ARM Cortex-A9 cores and a 1 GB DDR3 DRAM and the PCIe Gen 2 interface. So it's similar with the existing OpenSSD. And the second platform OpenFlash can run is Xilinx Kintex UltraScale FPGA. It has PCIe Gen 3 and 4 GB DDR4 DRAM. So this figure shows the hardware prototype of OpenFlash. The large board is the FPGA development board, and the above 2 small cards are FMC-based flash cards. So far, OpenFlash has the following specs. We have 4 channels, and each channel has 4 CE or 8 CEs. As a result, OpenFlash right now can support 512 GB or 1 TB capacity. The processor used in OpenFlash is a 9-stage pipeline double issue 64-bit RISC-V processor. The right figure shows the architecture of our developed processors. It includes the front end, which consists of iCache, Dcache, decoder, and branch predictor. The back end of the processor includes the pipeline, the load store unit, and the multiply division unit. So you can see we have the NAND flash interface with the OnFi 2.1, and we use the BCH ECC encoding. Right now, we have some preliminary results for the OpenFlash performance. The bandwidth can reach to around 500 megabytes per second, and the IOPS can reach to 100 kilo IOPS. We also developed 2 types of firmware. One is for the conventional SSD, including page level address mapping, garbage collection, and data caching. We also build a mapping table cache for our page mapping, which is used to save limited DRAM space. The second type of firmware is for DNS SSD. We develop zone mapping and management functionalities in this type of firmware. This figure shows the architecture of our developed flash controller. We designed 4 hardware channels to process read, write, erase commands. We also designed 1 queue for each channel, which is used to execute the request scheduling when serving incoming commands. In addition to the hardware channels, we also designed a software channel. This is used for debugging firmware, and we can execute single-step operations by using this software channel. We designed the flash controller as an extensible framework. Based on this framework, we can easily add new functionalities to the controller. For example, we implement multiplying operations, suspend erase, partial read and write into the controller. So this is the architecture of OpenFlash and the current status of OpenFlash. So now OpenFlash can run on the FPGA platform. We can use OpenFlash to explore some research issues. So next, I will introduce two explorations we are taking by using OpenFlash. The first one is exploring DNS SSD. As I mentioned earlier, DNS SSD provides sequential writes inside zones. DNS SSD can erase a zone without executing internal garbage collection. This can completely reduce the internal garbage collection of SSD, which is a very attractive feature. When using DNS SSD, one needs to place data according to its ownership or its lifetime. For example, in the left figure, you can see we place the data belonging to application 1 in a few zones, and the data belonging to application 2 and application 3 are placed into different zones. If the data in a zone become invalid at the same time, then DNS SSD can erase the whole zone completely. So usually we prefer to class the data according to its lifetime instead of its ownership. The right figure shows the software ecosystem. We can see the software ecosystem also adapted to DNS SSD. For example, the device mapper in the kernel, it has a DM zone for DNS SSD. And we also have file systems like the F2FS and the ZoneFS, which can also run on DNS SSD. However, DNS SSD still has drawbacks. For example, it is still hard to handle small random writes. We take F2FS example. The main area of F2FS is its data area, which can fit into zone layout. However, the metadata area of F2FS, including superblock, checkpoint, net tables, incurs small random writes. So this area cannot be placed in sequential zones, as it cannot be only written sequentially. We have a few approaches that can address this issue. For example, DNS SSD provides zone random area, ZRWA, which can receive random writes. But this feature is still a proposal in DNS specification, which is not a public standard. DNS SSD manufacturers are also exploring this feature when implementing DNS SSD. The second approach is to use a DNS SSD, including a conventional namespace and a zone namespace. This is what Western Digital DNS SSD does. The conventional namespace works like a regular block device, which can support random writes, and the zone namespace still adopts sequential writes. This figure shows how such DNS SSD works. We can put the metadata area of F2FS in the regular block device provided by the conventional namespace and put the main area to the DNS devices. This is the second approach. The third approach is to use an extra conventional SSD to hold the metadata area of F2FS. And then meanwhile, F2FS use DNS SSD to hold the data area. This approach is what F2FS currently does for running on DNS SSD, but it introduces extra cost as it needs an extra SSD for running F2FS. This is costly. So the second approach I just mentioned seems a good solution to run F2FS on DNS SSD. However, we run experiments to test the interference between the conventional namespace and the zone namespace. These two figures show the result. The left figure shows the result when we send a large granularity sequential writes to both conventional namespace and the zone namespace. As you can see in this figure, the blue ones are the performance of zone namespace, and the red ones are the performance result of the conventional namespace. As for serving large granularity sequential writes, the conventional namespace behave a little worse than the zone namespace, as the gap is a little small, relatively small. However, the right figure shows the performance result when sending 4 kilobytes random writes to both namespace. At this time, as you can see in the figure, the performance of conventional namespace decreases a lot, as the gap is large. the gap between the blue one and the red one is large. So this means even if we use conventional namespace in DNS SSD, we still face the challenges of traffic interference between the two namespaces. So in our research exploration, we propose a lightweight block layer based on DNS SSD. We use a block layer to convert random writes to sequential writes. In order to let the block layer work with the crash consistency, we fully utilize the out-of-band area, which is the OOB, out-of-band area of each page inside the DNS SSD. The block layer writes user data and the block mapping in an atomic way into a page. The out-of-band area of each SSD is used to store mappings between the logical blocks and the zone offsets. In addition, we also use the OOB area to store ECC code and the GC metadata. We implement this block layer on OpenFlash, and the space area provided by this block layer can be written in a random way. As a result, we can run F2FS on a DNS SSD without requiring the conventional namespace. So this is the first exploration we are doing on OpenFlash for optimizing DNS SSD. The second exploration is related to near data processing. The left figure shows the internal architecture of the SSD when used for near data processing. As you can see in the left figure, where we have hardware accelerators or multiple CPU cores, they are used to run offloaded processing tasks. The right figure shows the basic procedure of near data processing. The library on the host side can send the offloaded program code to the into the SSD, and the SSD internal runtime runs the offloaded code on CPU cores. After calculating the result inside the SSD, the runtime only needs to return the final result to the host side without transferring the data. This can save communication cost between host and SSD. However, since program code can be offloaded into SSD, it introduces potential security problems. This is because SSD internal also runs FTL firmware. The offloaded program code can equally access the memory area of the FTL firmware or steal the data. So we need to guarantee the security of computational SSD. Actually, what we are doing is to build a trusted execution environment for the RISC-V processor inside OpenFlash. We implement physical memory protection in our developed RISC-V processor. This helps to protect FTL firmware from illegal memory access. For other offloaded program codes, we also implement a runtime for near data processing. As you can see in the figure, both the runtime and the FTL run in machine mode of the RISC-V processor, and the offloaded program codes run in the user mode. The PMP mechanism provides memory isolation between FTL firmware and offloaded codes. In order to provide data integrity, we also implement data encryption. In RISC-V processor. Here we implemented the memory encryption. So far, we take a few preliminary evaluations on the trusted execution environment that we implemented in the OpenFlash. We use two NDP programs. One is to calculate the histogram for fetched data, and the other is to compress data. As shown in this table, the memory encryption in our developed RISC-V processor only introduce a little overhead, which costs less than 1% IPC reduction. The overhead is small. Okay, so these are two explorations we are taking based on OpenFlash. Okay, so now let me conclude my talk. In this talk, I introduced OpenFlash, which is an open source SSD controller platform. Because hardware, software co-design, domain-specific design, and near data processing are major concerns from both academia and industry, we want to provide a real SSD platform to enable efficient implementation and evaluation for SSD-related innovations. So we hope you can use OpenFlash for your research work and for your customized development. Okay, that's all for my talk. Thanks for listening. I'm ready to take questions.